All right, our next speaker, by special invitation, James Jackman, and he'll be talking about the physics of stellar flares, an overview.
Joke. And you can all see that, I hope.
All right, class, quiet down, please.
I hope I have everyone's full attention. Okie doke, if we're ready to go, then I'll begin. So, hello everyone, my name is James Jackman. As has been mentioned previously, I'm a postdoc at Arizona State University, and I've been working with the Red Dwarf Flare team to study stellar flares on low mass stars. And I've been invited to talk to you today about kind of what's actually going on during a flare, the physics behind a flare, and then what we can learn about the physics behind flares via the observations such as the team has been getting. So, well, let's jump straight in. What is going on? What is a stellar flare? Well, the one-line summary of a stellar flare is that it's an explosive phenomenon caused by a reconnection event in the magnetic field of a star. And shown here on the right-hand side is a kind of a cartoon of the standard model of solar flares. And stellar flares are believed to be analogous to solar flares. Oh dear. In a reconnection event, so magnetic field lines are anchored into the convective envelope of a star. And as the convective envelope, you get the convective motions via turbulence, upflows and downflows. These magnetic field lines are moved around, these field loops, they move around, and eventually they're twisted, they're sheared, and up in the upper atmosphere of the star in the corona, the field lines are eventually kind of forced together. Oppositely directed magnetic field lines can't cross over each other. They're frozen into the plasma, and they're almost connected to that plasma. And if you try and force them into each other, they won't cross over. Instead, they undergo what's called a reconnection event, where this rapid cartoon on the right-hand side kind of shows what's going on. Magnetic field lines, oppositely directed magnetic field lines, as they're pushed together, they undergo an almost instantaneous breakage and reconnection, which then transfers them to a lower energy state. As they do this, they then move away, and the excess energy that's released when they transfer into that lower energy state is released into the surrounding plasma. This is released as a combination of thermal energy into the surrounding plasma and then kinetic energy of the charged particles in the surrounding plasma. And these charged particles are then accelerated and these non-thermal particles are accelerated down towards the chromosphere, back along the magnetic field lines. You can see these on the right-hand side with these spiraling, as they spiral along the magnetic field lines. As they do so, they emit microwaves via gyro or cyclotron irradiation. And these charged particles travel towards the chromosphere. Now, the chromosphere, the layer between the photosphere and the corona, the plasma of the chromosphere is much, much denser than in the corona. And as these charged particles impact the chromosphere, they are rapidly decelerated. As these non-thermal particles are rapidly decelerated, they release energy into the surrounding plasma. This dense chromospheric plasma is then heated, ionized, and evaporated. And the initial layers of the chromosphere are heated to temperatures of between 1 and 10 million Kelvin, almost as hot as Phoenix in the summer. And some of that plasma is then heated or evaporated and goes to fill the newly reconnected magnetic field loops. And you can see that by that red kind of arc on the right-hand side. These field loops, with a plasma temperature of 1 million Kelvin, emit strongly via soft X-ray irradiation. Now, stellar flares aren't just a 2D process. On the sun, you often see these loops, or you see these loops all kind of stacked up against each other in what's called a flare arcade. And an example of this is shown here on the right-hand side. X-ray observations of a flare arcade from solar flares. And you can see the points where they're kind of anchored back into the chromosphere. That's a kind of what's called flare ribbons, or it's a series of what we call flare foot points, these red circles you see here. Now, at the same time as the evaporation, in order to conserve momentum, because you have non-thermal particles traveling downwards and then you have a load of plasma moving upwards, we get what's called a chromospheric condensation. This chromospheric condensation is another intensely heated layer that then descends from the upper chromosphere down towards the photosphere. some studies suggest that this chromospheric condensation, as it descends, it cools down and releases energy into the surrounding plasma as it goes into the lower chromosphere and then the photosphere. And it's been suggested that it's the heating from this chromospheric condensation that may be responsible for the heating of the photosphere and then the emission of optical irradiation, or the bulk of optical and UV irradiation, by heating the photosphere to a temperature of about 10,000 Kelvin. I say some studies have suggested this because it's also been suggested that the photosphere may also be directly heated by those electron beams, by those non-thermal particles coming down from the initial reconnection event. As these electron beams accelerate down, they may punch straight through the chromosphere and reach down into the photosphere, directly heating and giving rise to that white light emission that we've been hearing about today. And the exact mechanism is still being debated. It may depend on it will depend on the strength of the electron beam, which in turn depends on the strength of the reconnection event, and also will depend on factors such as the plasma density. A denser plasma is going to put up more opposition to an electron beam, and in that case, it may be your white light heating is due to the chromospheric condensation, whereas a more rarefied plasma, the electron beam, will be able to get straight through to the photosphere. But regardless of the exact heat mechanism behind the heating of the photosphere, we know that in solar flares, the flare foot or the photosphere is heated up, and this gives rise to the bulk of the optical and then the ultraviolet emission. And its photosphere, or the photosphere around the flare foot points, is heated, as I mentioned, to a temperature on the order of 10,000 Kelvin. And I should also note that in stellar flare studies, it's typically assumed that the bulk of this optical and UV emission comes from the flare foot points. But again, there has been some suggestion that there may also be a contribution from those heated flare loops as that plasma cools down as well. But this depends on the size of the flare loop and then the density of the plasma within that flare loop as well. If it's quite a rarefied plasma, we may not expect a significant contribution. But it's typically assumed that the bulk of that emission in the optical and the ultraviolet comes from the heated and then the ionized plasma at the flare foot points, from the back heating of the photosphere. Now, when we observe solar and stellar flares, we observe slightly different things, or slightly different forms of observations. On the sun, as we know, we can spatially resolve individual flares. We can get lots of spatial information, often within narrow wavebands. We can't do this for flares from other stars. And you can see that on the right-hand side. You've got the sun compared to TRAPPIST-1, where the sun, you have this wonderful spatial resolution, and TRAPPIST-1 is about a handful of pixels. So for stellar flares, we have to get time resolved. We're limited to getting time resolved photometry and spectroscopy, and that's of the entire stellar disk. And we have to isolate the relative flare emission to try and probe the flare behaviors. And just examples of actual flare observations themselves. Again, on the top is a white light observation of a flare from the photosphere. I think this is in the helium infrared line and the 10830 angstrom line. And on the bottom is observation of a flare from a star from Kepler data. Now, the bulk of, in the flare literature, the bulk of stellar flare observations that we use for probing the amplitudes, durations, and energies of stellar flares comes from single filter photometry. This is due to the prevalence of data from wide field exoplanet surveys, such as Kepler and TESS. These studies observe tens of thousands of stars for almost simultaneously for months or even years at a time. With these observations, studies measure the relative flux of the flare, such as that shown here on the right-hand side, and use that to calculate durations, such as we've been hearing the T-half duration, the full width half maximum, flare amplitudes, and then also use these optical observations to calibrate models for calculating bolometric energies and in turn bolometric flare rates. This has been done and can be done for individual stars, such as that shown here on the right-hand side, but also for entire spectral types and as a function of age, shown here on the right-hand side, where a variety of different flare rate measurements for I think stars stretching from ultra cool dwarfs on the top left all the way down to solar and even higher mass stars, but down on the bottom right, and as a function of age as well, where the blue bins are for stars older than 50 million years, and the gray bins are for stars younger than 50 million years, showing that the activity decreases as a function of age. And then also, as we also heard earlier, these studies try and use stellar flare rates to understand the effects of flares on exoplanet habitability by comparing these flare rates to limits calculated from biological studies. Well, on the right-hand side here is now the flare rate of TRAPPIST-1, late M star, 0.1 solar mass M star with 7 Earth-sized planets around it, 3 of which are in the habitable zone. And the green region is a region on the flare rate diagram, the abiogenesis zone, where it's been suggested that flares could provide the near ultraviolet flux required for prebiotic photochemistry to occur. But at the same time, the yellow region is what is the ozone depletion zone, where coronal mass ejections that were thought to be associated with flares may strip away atmospheres. So these studies are trying to use this data, the single filter photometry data, to understand the effects of flares, how flare properties change across spectral types and with age, and the effects that flares might have on habitability. Now, the models that these studies use can be relatively simplistic. They often assume fixed temperatures and often will ignore the contribution from optical emission lines. The fixed temperature that they mention is one David Boyd mentioned earlier, or fixed temperature they use is one David Boyd mentioned earlier, temperature of about 9,000 Kelvin. And this is based off of optical spectroscopy of flares from active M stars. And this black body is used to describe the continuum emission from the plasma at the heated photosphere. But as I said, these studies, or this model, ignores the contribution from optical emission lines and temperatures higher than 9,000 Kelvin, such as we've seen today. So we need to get more and more observations to kind of test the accuracy of these models and potentially aid in the construction of new ones that will help our understanding of both flare physics and the effects of flares. There we go, we need new observations. And all kinds of observations are especially valuable, but particularly those covering long time baselines. Because larger observatories, as we know, they'll often not observe for more than a few nights. You have to get your application past the time allocation committee, and simultaneous photometry and spectroscopy requires multiple large facilities, which makes your application even harder. And long time baselines allows us to build up the samples of flares needed for probing a variety of different flare emission behaviors and for measuring flare rates. And all kinds of observations can be used to tell us something about the physics of flares. Multi-filter photometry can be used to measure pseudo-continuum flare temperatures. Photometry captures, as we know, captures both the continuum and line emission, any continuum and line emission that falls within your chosen filter. Color measurements of flares can be combined or can be used to fit black body temperatures too, and measure pseudo-continuum flare temperatures to better understand the heating of the photosphere. If these observations are sufficiently high cadence, we can get a better understanding of how the heating at the flare, how the heating of the photosphere occurs, especially during the flare rise, during the initial energy deposition. And this can tell us about the transport of energy through the chromosphere and the heating of the photosphere. Spectroscopy of flares alone can tell us a lot as well. Individual lines inform us of the energy budget in the optical. Shown here on the right-hand side is a plot from our team showing the emission showing flare emission in the Balmer lines. And these models, and this is a particular use to testing the assumptions of models that assume continuum dominated emission. Kind of get an idea of how much energy these models are actually missing out. And again, as we saw earlier, observations covering a wide range of wavelengths can be used to directly measure continuum temperatures. Showing, and again, David Boyd's plot shown here on the bottom, showing that you can measure temperatures higher than 9,000 Kelvin, resulting in higher amounts of UV emission. And also, observations, particularly of H alpha and H beta, or of the Balmer lines in general, can also be used to probe for coronal mass ejections, outbursts of plasma that are often seen on the sun emitted with high energy flares. By looking for Doppler shifted emission in the H alpha or H beta line, that is at speeds in excess of the escape velocity of the star, these observations can be used as evidence for coronal mass ejections. Oh, and there we go. And this observation is from archival SDSS data, which has a resolution of about R of 2000. But combined photometry and spectroscopy of flares is a particularly powerful tool. The photometry can provide high cadence measurements of the flare morphology, informing us of the impulsivity of the flare. And importantly, when combined with spectroscopy, it can tell us about the precise precise phase of the flare that a single spectrum may be obtained in. It can tell you whether a spectrum occurs at the flare rise, whether it occurs solely during the flare decay, or whether it's some combination of the two. This in then tells you about about the contribution of what your spectra is telling you about the initial heating or cooling of the photosphere, and so on. And then again, the spectroscopy, how do different emission lines trace each other in time? Do different emission lines from different regions of the chromosphere, do they lag behind each other? So there we are. High cadence photometry tells us about the impulsivity of the flare and tells us about the balance between heating and cooling. And how much models might underestimate average UV energies by. And again, spectroscopy can tell us how much energy is released in individual emission lines. We saw this in Bob's talk earlier by measuring flare rates for individual Balmer lines. And that can be compared again to current models that are being used in flare studies for calculating bolometric energies, and also for studying what's the dominant source of energy at each flare phase. As you have the initial heating and cooling of the photosphere, or the plasma in the photosphere, various elements are going to be ionized. During the flare decay, as that plasma cools down, we saw earlier that you have a lag, and that the Balmer series, as the plasma cools down, the Balmer series then goes into recombination, releasing energy during the decay. And it may be that, in fact, the accuracy of these models may vary as a function of flare phase. So these observations are really important for, again, testing the accuracy. And again, time delay of emission lines relative to the continuum and also each other informs us of the cooling timescales of plasma in the photosphere and lower chromosphere. Denser plasma regions are thought to result in more efficient cooling. And coronal mass ejections, don't forget about those. And all of these observations together are fantastic for studying the physics of what's going on, particularly at the photosphere, at those flare foot points. But when they're combined, they provide a particularly valuable tool. The spectra and the photometry, particularly multi-filter photometry, can be used for the construction of new flare models that can then be used by future studies for getting more accurate measurements of the bolometric energies of flares and the effects of flares on exoplanet habitability. But also these spectra can also be used, and the photometry can also be used as inputs and comparisons to RHD simulations. So RHD is radiative hydrodynamical simulations. Simulations that are trying to study intensely try and study and model the energy transport through the chromosphere and down into the photosphere from the impact or the energy injection from those electron beams that are accelerated down into the chromosphere. And these studies are at the moment trying to work out what electron beam energies you need to get the kind of super flares that we currently observe nightly on M-dwarf stars. So with that, I've hopefully convinced you, or throughout the day, hopefully been able to convince you that flares are important, and there's still a lot more that we need to learn. And with that, I will conclude. Thank you.
Okay, are there questions?
Dr. Jackman, I'm wondering, would there be any scientific value to adding time series polarimetry to the photometry and spectroscopy process on these flares?
I mean, if you're offering, we'll take it. But yes, it would definitely provide scientific value to understand what the polarization is, particularly of the initial heating. If I go back to where's it gone? The model. Yeah, if providing polarimetry would probably provide a quite a useful input, again, for those radiative hydrodynamical models that want to understand almost everything they can get about the energy input into the chromosphere.
We have a question from online from Joyce Gusick. She says, this is slightly off the main topic, but I am often asked the question of the difference between a flare, a prominence, and a coronal mass ejection. Do you have a succinct answer to that question?
I have an answer. Answer yes, succinct, maybe no. So a flare is predominantly thought to be just the electromagnetic radiation. So you just have, we have the reconnection event, the charged particles coming down, and heating of the chromosphere, then the photosphere, and the plasma evaporates and then rises to fill this magnetic field loop. The coronal mass ejection, so not every flare has a coronal mass ejection. We see that on the sun, that often you can get low energy flares may not always be associated with coronal mass ejection. The coronal mass ejection occurs if this almost the plasma, so you see in this cartoon, as that X point comes together, if this plasma, if it's with high enough energy, if the plasma is almost, if the magnetic field lines are being forced up fast enough and the plasma contained within it is being forced up fast enough, that's when you can get a coronal mass ejection. When that plasma is moving with a velocity greater than the escape velocity of the star. But sometimes you get, so if I go, where's it gone? So there, in this coronal mass ejection, this is when you've had enough energy to almost push the plasma out. Sometimes, if there's an quite a strong overlying magnetic field loop, that can trap the plasma back in, and that results in failed coronal mass ejections as well. So coronal mass ejections are the plasma escaping itself. The flare is the general process and is dominated by the electromagnetic irradiation. And then the prominence, that one I'm going to have a think about exactly where that comes in. So it's, yeah, coronal mass, they are separate processes, but they're very intimately linked. But not every flare has a coronal mass ejection, and even potentially not even every coronal mass ejection has a detectable flare. There are things called stealth CMEs that can occur as well.
Hi, James. It's David Boyd here.
Hi, David.
Hi. Thanks for taking the time to come and talk to us. Given that you indicate that what we're doing is potentially useful, the data we're collecting, how would you suggest we can most effectively bring that to the attention of the people in the professional community who could make use of it?
So I think making publicly available archives, particularly of individual flares, so the archive that the group has been making to store the spectra and such for individual flares, that's a fantastic step towards that, to build almost a publicly available archive of flare events and then make sure it's intimately detailed. That's like a publicly available database that stores all the data, all the spectra and photometry of individual flares. That'd be a fantastic resource, or that is a fantastic resource. Also, on a more kind of networking side of things, presenting this work at conferences such as the AAS, where you have more professional astronomers, and then emailing more professional astronomers as well, saying, we have this big database, is this something that you would be interested in?
Okay. Is the level of presentation you've been hearing this morning the sort of thing that would go down well at an AAS conference?
Yeah, I reckon if the group puts together, I think the group would be able to put together maybe one talk for the AAS. I'm not sure we'd be able to get away with 3 talks.
No, that'd be too greedy.
Yeah. But almost a talk that is an advert for the group saying, we have this data, this is what we've been doing, we can do this. We invite like collaborations with professional facilities, like come and talk to us. Then that would be a great way for highlighting to the people running these RHD simulations that the data is there and it can be used.
Right, thanks for the advice.
Yeah, I will also have there's a few people I have in mind that I will email as well to ask what their opinions are, because they may turn around and say, we want it in this exact form, in this exact way, which is useful information to have.
Other questions? Oh,
We
online?
have another online.
Okay.
I'm going to go ahead and ask Nick to unmute and go ahead and ask his question. Nick Dunkel online, go ahead.
Thank you. Your paper and several other papers have talked about the benefits of using photometry along with spectroscopy. Can you explain to someone not into spectroscopy like me why you cannot just sum up the wavelength channels of your spectrometer and use that for photometry, especially with the advent of the CMOS cameras that don't penalize you for reading them out quite often?
So there's a question asking whether, so with spectroscopy, you get, spectroscopy is where you get the really very important information about the line emission. If you sum up all of that, you will lose that for stellar flares. You'll lose your information about the Balmer lines and then how those may vary with respect to the continuum. So I'm not sure I quite understood the question.
We might let David Boyd weigh in and explain how we get our flux calibration, which is a little different than how the pros do.
We're getting our flux calibration by taking photometry and then using essentially using the magnitude as a measure of the absolute flux through that filter passband, and then using that to scale relative flux spectra up to absolute flux spectra. Is that an answer to the question?
If that's not an answer to the question, I feel free to email me or anyone in the group, and we'll be happy to answer it offline.
Any other questions? All right. Thank you so much, James.
Oh, my pleasure.
Thank you for letting me twist your arm into this, James. Great.
That's okay.